So consider the side view of the solenoid. These are the different turns, are the different lines, and we want the dipole moment to be aligned with the magnetic field. So if we assume that they're both moving to the right, that means if I use the right hand rule, I want to wrap my fingers around the solenoid so that my thumb is pointing in the direction of the magnetic dipole moment. So we're going to do this a little bit opposite. We're going to put our thumb pointing to the right, and then the natural curling of our fingers will tell us where the current is. And hopefully after you examine this a few times, you'll notice that the current has to be coming from the top to the bottom. Your fingers, if they curl from the top to the bottom, then you can get your thumb to point to the right. You can have them go also from top to bottom, but your finger points to the left, but that's not aligned with what we need. So it has to be from top to the bottom. So we found the direction, and now we want to find out what the work is. And the work, as we know, is the change in energy, in this case potential energy. So we're going to say it's the final potential energy minus initial potential energy. And since we have two different alignments between that we're looking at, then we can say that this is the potential energy at 90 degrees minus the potential energy when they're aligned, which is at 0 degrees. And the potential energy is the dipole moment dotted with the magnetic field. So this would be two dot products, but one at 0 degrees and one at 90 degrees. So this would be mu b cosine 90 degrees minus mu b cosine of 0 degrees. And so this would be mu b actually these should be minuses here. Sorry about that. It's mu. So this would be 0, right? Because cosine of 90 is 0. And then I have a minus minus, which turns into a plus. And now the work at, we know that mu, the magnetic dipole moment, is the number of terms times the current times the area. So in this case, the work, which is mu b, is going to be NIA b. And if we plug these numbers in, we get 250 turns times the current, which is 100, 10 to the minus 6 amps, times the area, which is 2.52, times 10 to the minus 4 meters squared, and the magnetic field is 0.85 Teslas. So that gives us a work of 5.4 times 10 to the minus 6 joules, which is what we were asked to find.